Even though we don't know what dark matter is, we kind of see its effects. In a way, dark matter is quite easy to model. It basically only interacts gravitationally. So if you know Newton's law of gravity, you can actually describe and predict what dark matter is going to be doing. However, dark energy is much more puzzling. And perhaps to understand why that is and why we only discovered it in around 1998, we should probably look at some of the fundamental observations. In section 9, we've seen that stars like the sun, when they run out of helium, they essentially get a core full of carbon and then nothing else happens. They become white dwarfs. Now, these white dwarfs can actually accrete more gas. For example, if this white dwarf is in a binary system. Now, if this white dwarf reaches a mass of around 1.44 solar masses, it actually gets hot enough that it starts fusing carbon. And this actually leads to a very quick chain reaction that produces enormous amounts of nickel 56. The problem with nickel 56 is that it's radioactive and very quickly decays, releasing huge amounts of energy. This leads to something that we also call a supernova, but it's a supernova 1A. It is not the end of a massive star, but rather this nuclear detonation of white dwarfs if they get massive enough to trigger the fusion of carbon. Along the years, people have been looking at essentially the light curves of these supernova 1A, and they've realized that essentially just before the nuclear detonation, their absolute magnitudes go up by quite a lot, and then they actually decay as time passes. This is in terms of days. Now, I think one of the most spectacular things is that because we understand that this is the radioactive decay of nickel 56 until it gets to iron, we can actually calculate what is the half-life time of nickel, and it matches incredibly well with these curves. Of course, what we also realize is that not all supernova 1A actually have exactly the same width, and also some of them actually get more luminous. Others are not so luminous, but it seems like this essentially the time that it takes for them to get to peak and then to come back to the same sort of absolute luminosity is related with how luminous they actually get. So it is possible to transform these light curves into something that actually applies to every single supernova 1A, and that is very well modeled, essentially by our knowledge in the lab of radioactive decay. So with very simple nuclear physics, we can actually interpret light curves of these distant supernova. One thing you should definitely be asking is, what do these supernova have to do with dark energy? I mean, they're not powered by dark energy. They're powered essentially by a chain reaction that leads to the production of lots of radioactive material that then radiates as it decays. However, once we realize how we can standardize these things, we can actually use them as standard candles, essentially as distance indicators, because once we standardize them, then the peak always occurs at, say, 19.5 in the B band. And therefore, we can compare the apparent magnitude of one of these supernova with the absolute magnitude that we think it has, and that allows us to measure a distance directly. If we do that experiment, and essentially using this equation that we've covered before and used many times, we can measure a distance, say in megaparsec. What we can also do, and these supernovae are so luminous that we can see them in very, very, very distant galaxies, we can measure the redshift up to that galaxy, and then we can compare the redshift versus the actual distance. The reason why this is so interesting is because we can actually compare the prediction from the Hubble law that tells you that the more distant the source is, then the higher the redshift, with some actual observations. And this is what was done that led to the Nobel Prize for the discovery of evidence for dark energy. And the way that you do this is you find a supernova 1A at different redshifts, up to, say, redshift about 1. And then what you can also plot, so these are the actual data points, the red with the error bars. And then what you can do is compare observations with predictions of, for example, what you expect if the universe was just made of matter. And in that case, the universe would probably be bouncing back and contracting again, versus models where you can have, say, cosmological constant, where the universe is forever expanding, or where the universe is even accelerating the expansion. And if you plug in a model with about 75% dark energy, this is what you get, which is the model that best describes observations. And definitely, even in the early days, observations were very, very far away from a universe that contained just matter. But all you're really doing is applying the knowledge that you've covered in Physics 263, measuring an apparent magnitude at peak of the supernova 1A, predicting what is the absolute magnitude of this supernova 1A. This allows you to measure a distance. If you then measure the redshift, you can make a plot like this, and you can use your cosmological models, which you will start covering in Cosmology 1, and actually make a discovery worthy of a Nobel Prize. It is nonetheless important to point out that observationally, what we're seeing is as we move up in redshift, then these supernova 1A are actually fainter than we would expect. Essentially, their apparent magnitudes are higher, meaning fainter fluxes, than what we would expect. And we are interpreting these observations, fainter fluxes, as evidence for D supernova 1A being more distant than we expected. And this is where the evidence for an accelerated expansion comes from. If we find that things are actually even further away than we would expect, a way to explain it is that the universe has been expanding even faster, so that these supernova 1A are much more distant than we would expect. But there was, of course, a lot of discussion interpreting these observations, especially because a source that looks fainter than it is could be explained by, for example, more distant sources containing more dust. But all those alternatives have been ruled out. Many more measurements have been added to this plot that led to the Nobel Prize. And we are very confident that they really are much more further away than we would think. And dark energy, or the accelerated expansion of the universe, is the leading explanation for these observations. Because we have very little idea of what dark energy is and what it's doing, it is not surprising that billions of pounds throughout the world are being injected in experiments that will try to constrain the nature of dark energy and try to understand what it's doing. One of the leading hypotheses is that dark energy is some sort of cosmological constant, and that dark energy has actually been there since the beginning of the universe. And without going into too much details about what this plot is telling you, but at least conceptually, you can probably understand that this is sort of the early universe. And we think that dark energy might have been there at the same level, but the key difference is as the universe evolved and it got cooler and cooler, then the importance of radiation and matter in the overall behavior of the universe kept getting less and less important, and we're now at a time in the universe where the effects of dark energy are felt very, very strongly, just because the effects of matter and radiation keep going down, but we think that the effect of dark energy is sort of constant. So in the early universe, we expect dark energy to have done very, very little, but as time goes on, we expect dark energy to become more and more dominant in the dynamics of the universe. Of course, many people are not convinced with the existence of dark energy, and technically we could just think that if supernova 1A are more distant than we think, it could be because we have something wrong with gravity at large scales. For example, let's just say that gravity goes as 1 over r squared for short distances, but perhaps for incredibly large distances, mass flips and somehow particles become repulsive. It's kind of a crazy hypothesis, and it's not really pursued exactly on these terms, but it is possible that what is happening is we got gravity wrong, or perhaps there's still something wrong that we missed up to now. And pursuing these hypotheses is actually crucial to the way that science works. If everyone is just working on one specific leading hypothesis, then it is possible that we'll just become blind to something that actually works better, or that may be closer to the truth.